I'm Dmitry. I'm principal engineer at Dropbox. I work on Dash with Eric here. So we're going to talk about how we use DSPy to some of the prompt optimization projects that we do for Dash. So first, as you may know, Dash it uses enterprise search underneath, so it's a search product with AI. But in order to optimize the search engine uses traditional ML. Even with all this language model that we have right now, we still need a ranking model in search because there's millions of documents to rank. And in order to do this model, you use a machine learning toolkit before large language models that will optimize relevance. In order to optimize, you need a lot of training data. So in the old days, what we would do is hire a bunch of human judges that will annotate all these relevant and relevant documents for a bunch of queries. Nowadays, we don't. We use LLMs. But then the question is, so LLM basically generates training data, then you train the ranking model, and then you run it. But then the problem is, how do you know that it works well? So that's where you start thinking about how would they, like if I hired a robot judge, or what if I hired a human judge? I would have to train it first. I would have to tell it, these are the guidelines, this is how you would label relevance for a set of queries. And then when they train, and then it would scale. So this kind of creates this loop for, first you calibrate the LLM judge with a bunch of a smaller number of human labels. In our case, it's maybe 1,000 fraction of the labels that get human reviews, and then through prompt tuning and optimizations, as we talk later with using DSPy, we get it to agree as much as possible with the human labels. But turns out actually even humans don't always agree with themselves. So with LLM prompts, even the smartest LLM is not necessarily as smart, but it's consistent. So you still have to tweak. 80% of case it will be correct with a little effort, but then the 80% of effort goes to optimizing the last 20%. Anyway, so when you calibrate the LLM judge, then after that you can scale it so that to generate the training data for the core relevance models for search. And that the process continues because you sample more data in it, right? So there are two kinds of problems we have to do. First is to get the LLM judge to agree with the humans. That's similar to you look at the disagreements and you measure the quadratic mean square error. In our case, it's normalized just because we use brain trust and it requires 0 to 1 scale. So we just scale. But basically, when it's perfect match, then there is zero error and it penalizes the biggest disagreement. So what you want to do is avoid the biggest disagreements. The other part of the problem is related not with just reaching the agreement, but also with when we want to try something that similar to Shopify, that he used the Quen or some smaller model that is cheaper in order to scale to a lot more labeling. So in our case, open source models or open weight models. And Eric is going to talk more about that. In that case, part of the problem is not only the agreement, but also trying to get it to be consistently outputting the right schema for the output. All right.
Cool. Okay. Thanks, Dmitry, for the intro. Thanks. Okay. What I'm going to do now is talk about the scaling bottleneck, and then I'll dive into a couple case studies. So our initial judge was built on the best reasoning model available at the time. That was OpenAI's O3 model. So it was very high quality, but it was also high cost. So that meant we could only label a small fraction of the query document pairs that we wanted to. So what we wanted to do was move to a smaller, cheaper, open weight model so that we could scale 10 to 100x at the same price point. The problem here, though, is that when we tried to just use the O3 prompt directly with a different model, it didn't translate well. So the performance just wasn't good enough for us to feel comfortable shipping something to production. So that's when we started taking a look at DSPy. We didn't want to do many rounds of like ad hoc manual prompt tuning. Instead, what we did is we define things as an optimization problem. In our case, we have a fixed task, so that's assigning a relevance label from 1 through 5 to query document pairs. We have fixed data, so we have a small corpus of human annotated examples, and our metric here is minimizing the normalized mean squared error between the LLM ratings and the human ratings. So fundamentally, this is an alignment problem. And if we had an NMSE score of 0, that would correspond to LLM ratings perfectly matching human ratings. So they'd be indistinguishable. Okay, cool. So let's dive into the first case study. So this is about scaling with GPT OSS 120B. So we optimized GPT OSS 120B for a relevance labeling task using DSPy's GEPA optimizer. I included a rough code snippet. This isn't quite what we use, but it's very close, of how we structure the GEPA feedback. So we can see at the top that what we do is we, in plain text, have strings showing, okay, like here's what you predicted, here's what we expected, here's like the delta. We have a human explanation below that. So this is like the human rationale for why they labeled and kind of like rated a query document pair as a certain rating. And then we have like the model's reasoning for why it gave its rating. So the intuition here is that like when they diverge, the reflection LM can take a look at both of them, compare it, and then optimize the prompt so that like it minimizes the difference between the two. I also have some control text at the bottom. This is very important. I'm going to be talking about it more in the next slide. But the general idea is kind of around avoiding overfitting and keeping the task parameters stable. Okay, cool. So yeah, so this is about the control text. So this is about like explicit constraints to prevent like cheating in the DSPy GEPA optimizer. So the problem here is that what we saw is that a lot of times it would start including example specific content. So it would include like exact quotes. So exact like, usernames, exact terms. Sometimes it would include very large chunks of the documents themselves. So this would be good for the training loss, but not good for the validation loss. We also found that sometimes it would even change the task parameters. So the rating scale is 1 through 5, but it actually changed the rating scale to say something like 1 through 3 or 1 through 4. It actually kind of makes sense because the objective that we're using here is normalized mean squared error. So it's really penalizing when like the model differs a lot from the human explanation. So basically, if you change like the rating scale from 1 through 5 to 1 through 4, you eliminate the possibility of like the largest disagreements. So it kind of makes sense, but it's just, yeah, it's just not ideal. Okay. So that's why we have like the explicit kind of constraints in the feedback below. In the feedback I showed in the previous slide. It helps regularize it and kind of prevent that type of like overfitting. I guess the analogy here is like with regularizers and classical machine learning. It's kind of like additional structure you add to prevent overfitting, but this time kind of like in the prompt space instead of the weight space.
Could you go back so we can see it now that you've explained?
Yeah.
Thank you.
Yeah. So yeah, we include text around like the exact examples, keywords, and not changing the basic parameters of the task. The last part is like about, this is more like relevance label specific. So this is about trying to like add a general rule to like an execution plan rather than kind of saying like, okay, specifically for this document with this title, rate it this. Okay, cool. So what kind of results did we get? Well, so we saw a 45% reduction in normalized mean squared error from our hand to baseline. We were able to reduce the normalized mean squared error by a pretty huge amount. We have like the comparisons with MePro v2 and GEPA. We see that MePro v2 is slightly worse than GEPA, still very good. But what we don't include here is also like the prompt lengths. So it turned out that the MePro v2 prompt was quite a bit longer because it would do like embedded few shot demonstrations. So GEPA was actually able to get like better performance with much lower token usage, which is pretty important when you're running inference at scale. Okay, so yeah, we were also able to up the scale by 10 to 100x. So GPT OSS 120B plus DSPy enabled us to label 10 to 100 times as much data as O3 at the same price point. And I think this point isn't talked about as much, but also very important. It's that the model adaptation time plummeted. So previously, if there's a new model, we have to, take a look at it. We have to do a lot of prompt surgery on it. It takes quite a while. Maybe there's regressions and we kind of fix them. But when we fix them, it introduces other regressions. With DSPy, it's a lot easier. For the most part, it's kind of like a one-line string change. Not exactly, but close to it. So we're able to reduce the model adaptation time for new models by a huge amount. Okay, cool. Let's dive into the next case study. So this is about operational reliability with a much smaller model. So previously we were talking about GPT OSS 120B. This is Gemma 312B, so model 1/10 the size. So when you're working with really small models like this, alignment is only half the battle. So before you even talk about alignment with human ratings, you need to make sure that the relevance judge is outputting valid JSON. It turns out that when we're using very small models like this, that's really not something you can expect. In our initial baselines, we actually saw that around 40% of the model's responses were malformed JSON. So even if we had the best ratings in the world, they're kind of pointless because we can't even parse it. Okay, so we tried applying DSPy to Gemma 312B, and we were actually able to see a huge drop in the malformed JSON. We were pretty impressed with how much DSPy was able to reduce it. We saw an over 97% drop in the malformed JSON. You can see actually in the slide, I have these bars. I can't even put the invalid format inside the bar because the sliver is so small now. But yeah, so what we saw here is that DSPy approved the alignment, and also it made smaller models operationally reliable. And even though Gemma 312B wasn't strong enough for production use, DSPy let us just try it out without a significant engineering investment. And so I think this is one of the best parts about DSPy is if a new model comes out, we can just try it. Previously, it's a lot more of a decision about whether it's worth the engineering effort to invest and all the prompt tuning and setting it up. Now it's just try it, see what happens. If it works, great. If it doesn't, no problem either. Okay, back to you, Dmitry.
All right, this is another example that we hit with when we were using DSPy. When this is not with the open source model, but with a strong reasoning model, when the baseline prompt is pretty good already, it's kind of close to your optimal maybe, and you're just trying to address some small nuance that's still available in the data. Then you want to kind of try to constrain the space that the DSPy uses for optimizing the prompt, so that it makes small changes, doesn't try to rewrite the whole thing, because it changes the whole problem. And more likely that it will be degradation in performance. So it's there's many different combinations of the prompt will just be worse. So in order to do that, what I tried is build a set of I see all the remaining disagreements in the data set, and I build bullet point instructions from each one of those, and then let DSPy optimize selecting of those. So those bullet point instructions it's not necessarily a huge space, but doing a power set of all of those is still hard computationally. So if you let DSPy do selection of these bullet points, it can improve things. So in this case, the core prompt is left alone, so it doesn't see how to optimize it, but it then does selection of the set of tools available as small changes to the prompt. So this gave us some improvement on the best model. So right. And to summarize, we have found two patterns for when DSPy becomes very useful. One is for, as Eric mentioned, was when we select smaller, there's always new models available. There's smaller models, cheaper models, and in this case, you want to do alignment of the of the model with the prompt using DSPy. And the second part is when we have a strong prompt and you need to fine tune it kind of, then it's better to do more constrained optimization using something like what I did with bullet selection. And in summary, the whole management of the prompt and the evolution of this becomes part of the engineering process that we do for Dash. So it's not just you do optimization once and you have the product requirements change, the users learn how to use the product differently. They will give you different examples where you need to address that you haven't seen before. And this whole thing needs to be repeated multiple times. And in order to do that, it's actually really hard to tweak things by hand. Like it's not like it's like in the old days we would tweak relevance models by hand. That doesn't work anymore because it's too many parameters. It's the same thing here. Then you would apply DSPy to optimize the prompt, and you kind of watch for the data, get more examples, get more samples, and iterate.